Hi boys and girls, this is lecture 6.4, the topic inverse functions. Let's revisit the definition of inverse functions. A function g is the inverse function of the function f if f of g of x equals x for each x in the domain of g and g of f of x equals x for each x in the domain of f. In other words, if we compose the two functions and get x as the result, then the two functions are inverse functions of each other. The inverse of the function f is denoted by f inverse, f to the negative 1, and this definition gives us a way of verifying whether or not two functions are inverse functions. Let's use this definition to verify that these two functions are inverses of each other. We'll need to show that f of g of x equals x and that g of f of x equals x. In composing these functions for the first step, I'll need to insert the entire g of x function in for x in the f function. So this is going to be 2 times the cubed root of x plus 1 over 2, quantity cubed minus 1. Well, the cubed root cubed, those two functions are inverses of each other, therefore we'll have a simplified form, 2 times x plus 1 over 2 minus 1. Of course, 2 and 2 cancel, giving us x plus 1 minus 1, which is indeed x. In this case, we'll take the entire f function and insert it in for x in the g function. This is going to give us the cubed root of 2x cubed minus 1 plus 1 over 2. And under the radical now, we'll have this simplified form, 2x cubed, since the negative 1 and 1 cancel, 2x cubed over 2, which reduces to the cubed root of x cubed, which is also indeed x. Therefore, we have verified that f of x and g of x are inverse functions of each other. Inverse functions have a reflective property as well. The graphs of f and f inverse are mirror images of each other with respect to the line y equals x. In this example, we're going to demonstrate the reflective property of these inverse functions. F of x equals 3x and f inverse of x equals 1/3 x. Let's graph the first function. I'll choose a few x values, 0, 1, 2, 3, and find the corresponding y values. I'll get 0 for this y value, 3, 6, and 9. Now let me plot these points. 0, 0, 1, 3, which is here. I'll also have 2, 6, which will be here. And then 3, 9 is going to be here. Now I have already graphed this line, so let's take a look at it. Okay. Now, when functions are inverse functions as these are, the domain and range are swapped. And so I can actually take these ordered pairs and just switch the x and y values in order to find ordered pairs for the inverse function. Let's test this in the function to see if it's true. Is it true that 1/3 of 3 is 1? Yes. Is it true that 1/3 of 6 is 2? Indeed it is. And of course 1/3 of 9 is 3. So let's plot these points and take a look at this line. We'll have 0, 0, 3, 1, 6, 2, and then 9, 3, which will be up here. And I have already graphed this line as well. Let's take a look at it. You can see that these two inverse functions demonstrate the reflective property. They are mirror images of each other with respect to the line y equals x. Notice that the inverse functions we previously verified also display this reflective property. Here is the graph of f of x, 2x cubed minus 1, and here is the graph of g of x, the cubed root of the quantity x plus 1 over 2. These two functions are symmetric with respect to the line y equals x. As it happens, not every function has an inverse function. A test for those that do, the horizontal line test for an inverse function states that a function will have an inverse function if and only if every horizontal line intersects the graph of f at most once. More formally, a function has an inverse function if and only if it is one-to-one. A function is one-to-one if for every x value there's only one y value and vice versa. Furthermore, if f is strictly monotonic on its entire domain, then it is one-to-one and therefore has an inverse function. A function is strictly monotonic if it is increasing on its entire domain or if it's decreasing on its entire domain. So let's use this test to determine whether or not either of these two functions has an inverse. Let's look at letter A. As you can see, it is strictly monotonic. It is increasing on its entire domain. Therefore, by definition, it's one-to-one, and it will have an inverse. Notice that if you draw horizontal lines anywhere on the function, it isn't going to intersect the graph more than one time. So it is passing the horizontal line test for an inverse, and it will have an inverse function. Now let's look at letter B. You can see that if I draw a horizontal line here, that it is not passing the horizontal line test. It's intersecting the graph more than one time, which means this function is not one-to-one and therefore will not have an inverse function. Guidelines for finding an inverse function. First, determine whether the function has an inverse by applying the horizontal line test. Second, solve for x as a function of y. X equals g of y, which will be f inverse of y. Then interchange x and y. The resulting equation is y equals f inverse of x. Next, define the domain of f inverse as the range of f. Finally, verify that f of f inverse of x equals x and f inverse of f of x equals x. Let's apply these guidelines in finding the inverse function for our given example. First, I'm going to rewrite the function replacing f of x with y. Y equals the square root of 2x minus 3. Since this is a radical function, I know that it is strictly monotonic, therefore one-to-one, and it will have an inverse function. Now I need to solve for x. I will square both sides of this equation, and that will give me y squared equals 2x minus 3. Adding the 3 over, y squared plus 3 equals 2x. And dividing both sides by 2, I'll have y squared plus 3 over 2 equals x. Now it's time to interchange x and y. Y equals x squared plus 3 over 2. And I'll replace y with f inverse equals x squared plus 3 over 2. So this is the inverse function. Let's verify that by composing the two functions. First, I'll find f of f inverse of x. F of f inverse of x will be the square root of 2 times the inverse that we found, x squared plus 3 over 2, minus 3. Let's see what this simplifies to become. F of f inverse of x then will be the 2's cancel, which gives me the square root of x squared plus 3 minus 3. Then the 3's cancel, giving me the square root of x squared, which is x. Now let's compose f inverse of f of x. And that will be x squared plus 3 over 2, x being replaced by the other function, the square root of 2x minus 3, quantity squared, plus 3 over 2. Squaring this square root gives me 2x minus 3 plus 3 over 2. These 3's cancel, resulting in 2x over 2, which does simplify to x. So we have verified that our two functions are inverse functions. Now let's discuss continuity and differentiability of an inverse function. Let f be a function whose domain is an interval I. If f has an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse is continuous on its domain. If f is increasing on its domain, then f inverse is increasing on its domain. If f is decreasing on its domain, then f inverse is decreasing on its domain. And if f is differentiable on an interval containing c, and f prime of c is not equal to 0, then f inverse is differentiable at f of c. The derivative of an inverse function. Let f be a function that is differentiable on an interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0. Moreover, the derivative of that inverse function, g prime of x, is equal to 1 over f prime of g of x, provided that f prime of g of x is not equal to 0. In this example, we're going to evaluate the derivative of an inverse function. F of x equals 1/4 x cubed plus x minus 1. We're asked, what is the value of f inverse of x when x is equal to 3? This question means that on the inverse function, what is the function value when x is equal to 3? So we're looking for the y value corresponding to an x value of 3 for the inverse function. Well, that means for the original function, we're wondering what x value corresponds to a y value of 3, this ordered pair. And you can see that on the original function, when x is 2, y is 3. Therefore, on the inverse function, the ordered pair 3, 2 applies. Therefore, f inverse of 3 is equal to 2. That's the answer to letter A. We're going to need that value to answer the question in letter B. What is the value of f inverse prime of x when x is equal to 3? Remember the way we're going to find that derivative. F inverse prime of 3 is equal to 1 over f prime of f inverse of 3. And of course, in letter A, I found that value, which was 2. So we're evaluating 1 over f prime of 2. We are going to need the derivative of f of x, which is f prime of x is equal to 3/4 x squared plus 1. Which means now I'm going to have 1 over 3/4 times 2 squared plus 1. This means I'll have 1 over 3/4 times 4 plus 1, which results in 1/4. So the derivative of f inverse prime of x when x is equal to 3 is 1/4. That's it for today's lecture. Speaking of symmetry, nothing compares to the artistry as well as the mathematical ability of our Creator. For the word of the Lord is right, and all his work is done in faithfulness. He loves righteousness and justice. The earth is full of the loving kindness of the Lord. Psalm 33, 4 and 5. God bless you, boys and girls.